Hello class, my name is Duncan Hasell. I'm in section MO3 with Dr. Greco. I made a video for our lab this week about an observation of rolling Red Bull can. One assumption that I made in the experiment is that Fnet is equal to 0, and I want to find out if that assumption is correct. So here's my video. I decided to make the origin at the center of mass of the can, and to make positive left, or the left x-axis positive and the right negative. So I used the diameter of the Red Bull can as a frame of reference for the whole frame. That's over here. It's about 5 centimeters, so it's 0.05 meters. So let's run the video and see what tracker says. And as you can see, the center of mass is tracked throughout the end of the video, and we get this graph over here that's pretty linear. It's not completely linear because of forces like friction, but it's pretty dang close. So next, I'll show you my VPython. Oh, this is the wrong thing. I'll show you my VPython. I found the mass out by a milliliter is equal to a gram, and it's a 250 milliliter can, plus I assume the can was about 30 grams, so maybe I assume the ball's mass was 0.28 kilograms, and the original position is 0, 0 because I started the vector as the can was moving. The can's velocity was 0.47, and I calculated this by taking the final velocity, or the final position and the final position plus minus initial position over final time minus initial time, and to find out the average velocity. So then the video lasted 1.125 seconds, so that's what I made it last. I assume the force net equals 0, and this line right here is kind of derived from the momentum principle. Just to remind you, the momentum principle is change in momentum equals Fnet times t, which can be changed to final momentum minus initial momentum equals Fnet times t, which you can move the initial momentum to the other side, this is the initial ball velocity, this is the final ball velocity. These two, the ball position just updates the ball position as it goes, and then t updates the time as it goes. Here, let's run it and see how it works. So you can see that it's a linear graph, it's moving to the right just like the can. Let's see, what else did I... this is a comparison of the two data collections. The blue dots is the data from tracker from the actual video, and the red is the linear velocity from the tracker, or from the simulation. It's a little, the blue is a little off, but I just attribute that to friction. I think it's pretty dang close to the actual assumed experimental or non-experimental calculated value. So then, what if we had done force? If there was a force acting on, if we just tried, like, if there was a force, oops, I guess you can't have a 0 in front of it. There's actual force. So it goes off in a random direction, not staying on the tabletop like we want it. So that shows that at constant speed or constant velocity, there is no force acting on an object. one of the questions that was supposed to be asked is it possible to calculate how many pushes and pulls are added together to give a zero net force? And I believe there is, as long you can calculate how many pushes and pulls are on the net zero force, as long as you have the right information to find this out. Thank you very much, and I hope you enjoyed my video.